Hello APC Mechanics students, in Unit 2 Newton's Laws of Motion, Class 14 Circular Motion, Part 3, Section 1, Acceleration of a Swinging Pendulum. Basically, in today's video we're gonna add also some nice applications on circular motion. An object of mass m is connected to a vertical light thread string, thus forming a simple pendulum. Let me do just some argumentations related to the motion of the pendulum before we move on. Now this pendulum is swinging left and right. Now at this particular point, the pendulum will change the direction, and instead of swinging up, it will be swinging down. So this is a turning point and the velocity is given by 0. Now here, at this particular point, we expect that the velocity of the pendulum would be maximum, and at this particular point, if you think about it, it won't be accelerating. Now at this particular point also, the object will lose speed, so the speed would be 0 because it will change direction. As it goes down like this, it will start speeding up. Reaching this point in particular, it won't speed up anymore. It will have the maximum value of speed. As it goes up, it will start to lose speed. It will decelerate until reaching here a speed of 0, and the motion is repetitive, so on and so forth. The equilibrium position is when the string is along the vertical. This is the equilibrium position. During the downward motion, the object is speeding up and has both acceleration centripetal and tangential. The tangential acceleration has the same direction of the velocity. Now in this one, during the downward motion, this object will be speeding up. We have two accelerations, centripetal and tangential, and the total acceleration would be like that. During the upward motion, the object will be slowing down and has both acceleration centripetal and tangential. The tangential in this case would be opposite to the direction of the velocity because it's slowing down. This is the centripetal, this is the tangential, and this is the total acceleration. And knowing that, the pendulum is moving up, and in this case it's moving down. At the equilibrium position, the object is not gaining speed anymore, then the object only has centripetal acceleration. So that would be the total acceleration because we have no tangential. At this point, it would attain the maximum speed. It won't be speeding up nor slowing down. So the acceleration is simply centripetal. At the extreme positions, the object has only tangential acceleration, and the centripetal acceleration is 0 since the speed of the object momentarily becomes 0. So remember that the centripetal acceleration is given by v squared over r. If the speed momentarily vanishes, that would be 0, which means the centripetal acceleration at the extreme position is 0, while it starts to gain some speed due to the tangential acceleration. Then the total acceleration would be the tangential acceleration. Loop the loop. A car is traveling, so this is another application, section 2. A car is traveling inside a vertical circular track. Through different points across the inner circular track, forces acting on the track have tangential and centripetal direction. However, we'll only now consider the forces acting along the centripetal direction, radial components. So at the point A, we might have other forces than the pull of gravity and the normal push, but I have only represented these two forces because they are along the centripetal direction toward the center. And if we need, okay, so let me now consider another point, the point B. At the point B, we would have the normal push toward the center. I won't represent the pull of gravity because it's not toward the center. At the point C, we would have the pull of gravity, which is down. The normal push is down because it would be perpendicular to the support. Remember that we might have other forces right, left, but I'm not representing them. And at the point D, we would only have the normal push. So now, for each of the following situations, after we have represented the centripetal forces acting along the center, I'm interested in writing Newton's second law version along the center. So Fn would be along the center, then Fn minus Fg would be mv squared over r. In this case, that would be just Fn is mv square over r. In this case would be Fn plus Fg is mv square over r. And in this case, that would be mv square over r. Example 1, the figure shows a cart moving over the top of a hill, case 1, moving at the bottom of a dip, case 2, and moving at the top of a vertical loop, case 3. In each cases, the normal force acting on the car is Fn and the weight of the car is Fg. In which case is it always true that Fn is greater than Fg, and in which case it's always true that Fn is less than Fg? And basically we're comparing the normal push to the pull of gravity, and this can be determined by referring to the center of the curvature, this is 1, 2, and the direction of the centripetal acceleration, which is pointing toward the center. If you consider case 1, this is the center, then the acceleration is down, we have the pull of gravity down, we have the normal push is up. Because the acceleration is toward the center, so we say that in case 1 we have that the pull of gravity is greater than the normal push. In case 2, this is the center, we have the normal push is up, the pull of gravity is down, so we can directly claim, because the acceleration is toward the center, that the normal push is greater than the pull of gravity. In the third case, this is the center, then the acceleration is down, the pull of gravity is down, the normal push is down. However, because both of them are pointing down, we cannot compare and we cannot claim whether Fg is greater than Fn or Fg is less than Fn. Now let's refer to the choices. In case 1, let me look at case 1. So in case we have the pull of gravity greater than the normal push, then it's either B or D. For case 2, we have the normal push is greater than Fg, then indeed it's B and not D. Now 3, minimum and maximum speed for circular tracks. In circular tracks like a roller coaster or going over a hill, the normal push Fn is the indication whether the track is safe or no. So remember that the normal push comes from the contact between the object and the surface. If the normal push vanishes, becomes 0, this means that the object will lose contact with the surface. So the indication whether an object will lose its contact or no is always the normal push. If the normal push Fn drops to 0, then the object in motion will lose contact. We anticipate that for a roller coaster, we would require a minimum speed to cross the vertical track. For a hill, there is a maximum speed that should not be exceeded. Let me explain more. At the top of a roller coaster, so this is a roller coaster, we have the normal push is down, the pull of gravity is down, then the equation is given by Fn plus Fg is mv square over r, then the normal push is given by mv square over r minus mg. If we start losing contact, then the normal push is 0, and if we replace the normal push to be 0, that would be mv square over r minus mg. Let me here repeat and say again why we have set this equation. This is coming from Newton's second law, F net is ma. We have the pull of gravity along the centripetal, so the pull of gravity and the normal push. Let's ignore other forces because we're gonna consider the centripetal direction. Along the centripetal, that would be toward the center is positive Fg plus Fn is mac, which is mv square over r. Now if we're about to lose contact, we will replace Fn by 0, and that would be mv square over r minus mg. Now we would cancel for m, then v is given by radical rg, but here the important interpretation, what does v represent? Is it a minimum or maximum speed? This is indeed a minimum speed, because if you have a roller coaster to be like that, and you're moving from A to B to C to D, so at D you might lose contact. In order for you not to lose contact at the point D, if you think about it, you should have some minimum speed in order not to lose contact, and this speed is given by radical rg. Going on top of a hill, the forces are given by the pull of gravity, the normal push, then our equation coming from, which is a linear equation coming from a vectorial equation, is given by minus fn plus fg is mv square over r. Fn is negative because it's pointing away from the center. And if you're interested in the case of losing contact, then we're gonna replace fn by 0. And if you cancel for v, also v again would be given by radical r over g, radical rg. But the thing here is that what is different from the roller coaster or loop-de-loop is that this speed would be interpreted as the maximum speed. Why? Because if you're traveling above the hill like that, you know that if you increase your speed enough, you might ending up doing a projectile. You might lose contact. So you can say that that would be the maximum allowed speed in order for you not to lose contact. If you're traveling inside a loop, that would be the minimum speed required for you to cross the roller coaster. However, if you're talking about the hill, that would be the maximum allowed speed for you to cover over the hill. Remarks: going inside a roller coaster of very large radius r would increase the minimum speed and v minimum radical rg required to pass safely without losing contact. So if the radius or the roller coaster is large enough, so the radius of the roller coaster increases, that would require from you a larger minimum speed in order to cross the roller coaster, and this is intuitive. Going over a hill with a very small radius, so if the hill is very narrow, which means the radius is very small, so let me try to approximate it even better. So that would be the radius r. So upon the hill to be very narrow, which means r decreases. If r decreases, means that Vmax is decreases, which means that the maximum allowed speed on this particular hill is so small, coming from the fact that the hill is very narrow. So you need to decrease your speed more and more in order not to exceed the maximum speed. Exercise 1. A sphere on the end of a string is released from rest at point X and swings through the point Y to point Z as shown in the figure above. Point Y is the lowest point for the sphere as it swings. Air resistance is negligible. 4 directions at point Y are indicated as 1, 2, 3, and 4 in the figure. Above, directions 1 and 3 are vertical, 2 and 4 are horizontal, and 1 is directed along the string. Which of the following best indicates the direction of the acceleration of the sphere at point Y? So we know that at point Y we have no slowing up or speeding down because the object or the sphere has attained its maximum speed. So the tangential acceleration would be 0, which comes from the fact that variation of the speed, and we only have centripetal acceleration, and that would be the correct answer, which is 1. Now the same question is repeated, but for point Z. We're interested in the direction of the acceleration at the point Z. We know that at the point Z, the object will momentarily lose speed, which means that AC, which is v square over r, that would be 0, so we don't have centripetal acceleration. However, going from Z to Y again, we know that the object will be speeding up and it will admit tangential acceleration, so the correct direction of the acceleration would be 3. Now exercise 3. A cart of mass capital M is approaching a hill with a circular top of radius r as shown in the figure above. The cart is carrying a load of mass capital M and is traveling with a speed v0. When it is at the top of the hill, the length of the cart is negligible in comparison to the radius of the hill. The cart never loses contact with the hill surface. The cart and load can be both considered to be at the same position. The speed v minimum is the minimum speed necessary for the cart and the load to leave the surface of the hill at the top of the hill. So here, let's hold on and let's take a look at the minimum speed. Now previously we were discussing whenever we're over the hill, we're talking about the maximum speed and minimum speed. Now I hope this might not confuse you in a sense. We were interested in determining the maximum allowed speed, but here they have reversed the question. They're interested in losing contact. For this reason, they're talking about the minimum speed necessary to leave the surface of the hill at the top of the hill. So we're interested in losing contact. For this reason, they're referring to the minimum speed. However, now whether we're doing this to be minimum or maximum, the expression would be the same, which is given by radical RG, which is mass independent. Now if the load is removed, if we remove the load, which means that the mass of the system will decrease, what is the new minimum speed necessary? We know that minimum and maximum speeds ain't affected by the mass. For this reason, it would be the same. Now exercise 4, a cart of mass m is approaching a hill with a circular top of radius r as shown in the figure. So basically it's the same figure here. So let me draw it. This is the cart, and that would be the load. The cart is carrying a load of mass capital M and is traveling with a speed v0 when it is at the top of the hill. The length of the cart is negligible in comparison to the radius of the hill. The cart never loses contact with the hill's surface. The cart and load can be both considered to be at the same position. In a free body diagram showing all the forces, not components, acting on the objects at the top of the hill, how many vertical forces will act on the cart and how many vertical forces will act on the load? We're just interested in the vertical forces, so any force which is left and right I will ignore. Now let me start by the load. What are the forces would be acting on the load? We have the pull of gravity down, we have the normal push is up. Now let's ignore the fact whether they are balanced or unbalanced. In fact, Fg would be greater than Fn because the center is down. So we have two forces for the load, then it's either gonna be A, C, or C. Now for the cart, we would have the pull of gravity down. We would have the normal push exerted by the hill on the cart, which is up. And there is another force exerted by the load on the cart, which is also down. So the cart would seize the load as a support, and the load will exert a force on the cart which is down, similar to the normal push. So that would be the force exerted by the load on the cart. So on the cart we have three forces, and basically C would be the correct choice. Exercise 5, a ball of mass 0.4 kg is attached to a light rope of length 1 meter. The ball is moving in a vertical circle as shown in the figure, with Earth's gravitational force as the only force external to the ball string system. The speed of the ball at the point P is 5.4 meters per second. So the speed here is 5.4 meters per second, and let me represent the string. The acceleration of the ball at the point P is most nearly. So they're talking about the acceleration. Do they mean centripetal, tangential, or tangential? The acceleration means the total acceleration, which is basically given by A is the square root or the Pythagorean sum of AC square plus AT square. Now we can determine AC because at the point P we have the speed, and here, although they mentioned that the only force is the force of gravity, but this is an external force, and you would have the tension force along the string, which is an internal force, which causes this sphere or the ball to make the circular motion. However, now no need to discuss in particular the tension, because we know the speed which is given by 5.4, so we can directly say that centripetal acceleration is given by 5.4 square, which is v square, divided by the radius r, and that would be 1, and the value is given by 29.16 meter per second square. Basically this is a very large acceleration. Now what about the tangential? The tangential in this case, it will be either up or down, and we can determine the tangential by referring to the forces acting on the point B at the point P. At the point P we have the pull of gravity which is down, so we can say that what's causing, or if we say F naught is MA, what are the forces acting on the ball at the point P? We have the pull of gravity, we have the tension is MA, and now we're only interested in the vertical direction. Now if up is positive, that would be minus mg plus 0 is ma. M cancels with m, so basically the acceleration, the tangential, which is along the vertical in this case, would be given by minus. Now the answers, they seem not to be perfect, so I will use tangential acceleration to be 9.81 meter per second square. However, here in this case, whether you have used tangential to be 9.81 or minus 9.81, that would be the same, because we will calculate the Pythagorean sum given by 29.16 to the power of 2 plus minus 9.81 to the power of 2. Plugging this on the calculator, we're gonna have an acceleration given by almost 31 meter per second square, and the correct answer in this case is given by D. Exercise 6. Car A can travel around a curved section of road without skidding at a maximum constant speed given by 10 meter per second. When car B travels around the same curve without skidding at a maximum speed, it has twice the centripetal acceleration as car A. The maximum speed at which car B can safely travel around the curve is most nearly. So we're talking about twice the centripetal acceleration, which means that we're interested in the factor of change given by AC is V square over R. Now remember that the factor of change method here works perfectly, unlike the Atwood machine, because the Atwood machine and the fractional mass, we have plus and minus. We're interested in the new maximum speed, so let's isolate for VV would be given by the radical of RAC. And now let's apply the factor of change. We didn't change the radius, that would be radical of 1. The centripetal acceleration is doubled, then the factor of change is given by radical 2. We're interested in the value, not the factor, so that would be the radical 2 times the initial speed, which is 10. Plugging that on the calculator, and the closest to our answer, 14.1 meter per second, that would be C. Exercise 7, which is the exit ticket for today's video. In the figure shown, a small object of mass m is spinning in a nearly horizontal circle of radius r at a constant speed v. The magnitude of the net horizontal force on the small object is F. So when the object of mass m is spinning in a nearly horizontal circle of radius r at a constant speed v, the magnitude of the net horizontal force on the small object is F. Basically, this force is the centripetal force, which is like that. The object is stopped, and then starting from rest, the object is made to spin in a nearly horizontal circle of radius r, so that it's speeding up with an acceleration a. This acceleration would be the tangential acceleration, which is like that, tangent to the trajectory. Here for me it's difficult to represent it because we're talking about two-dimensional photo. Which of the following expression is correct for the new horizontal force on the object? Pay attention here, they're talking about the magnitude of the force, which is F. So F is a magnitude. In order to add to F another force, which is basically given by MA, corresponding for the tangential force, this can be only done using the Pythagorean sum, because F and A are perpendicular to each other. If N and A are aligned or parallel or anti-parallel, we can choose C or D. But since they form a 90 degrees, one of them will be along the center and the other would be tangential, so we need to add them along the Pythagorean sum, and the only one confirms for the Pythagorean sum is E. Why we have multiplied by the mass? Because we cannot do like that, radical F square plus A square. This is force, this is acceleration. If we need the new net horizontal force, that would be the radical of F square plus MA square. Then that's it for me in this video, guys. See you soon in a new one.